In this video, we'll introduce polynomials. A polynomial function in one variable can be written as p of x equals a with a subscript of n, x to the n, plus a sub n minus 1, x to the n minus 1, plus, and that will continue down to a 2x squared plus a sub 1x plus a sub 0. The a's are coefficients on each of the terms, and n is going to be a whole number. That means n is an integer that is greater than or equal to 0. So 0, 1, 2, 3, and so on. N is also what we call the degree of the polynomial. Looking at this generic polynomial, the leading coefficient is a sub n. The constant term is a sub 0. Notice a sub 0 does not have an x beside it. That's why it's a constant. The domain of all polynomial functions will be negative to positive infinity, all real numbers. The graph of a polynomial we say is smooth and continuous. Smooth meaning there's no jagged edges like you saw with a absolute value function. Polynomials are smooth and continuous. Continuous means we can draw the graph without picking up our pencil. You'll get a more specific definition of continuous in calculus. The degree of the polynomial, as we mentioned earlier, is n. It's the highest power on x. Determine which of the following functions are polynomials. For those that are, state the degree. For those that are not, explain why not. For the polynomials, we want to also identify the leading term. F of x in this case is a polynomial. Notice that the powers on x are all whole numbers, or numbers that are integers 0 and bigger. So this one is a polynomial. We can state that the degree n is 2. It is the highest degree on x. And we can also state the leading term. The leading term is 3x squared. H of x is not a polynomial. Notice that you have a rational exponent, and we also have negative exponents, and we have a radical in it as well. All of those are reasons that make this not a polynomial. G, while at first glance may not look like the definition from earlier, if we expanded this all the way out, you would have a polynomial in the standard form that you saw earlier. This is a polynomial written in factored form. This has benefits that we'll look at later. So this is a polynomial. And imagine if we distributed this all the way out and removed all the parentheses, combined like terms, and we wrote it in descending order according to the powers. What would the degree be? What would the highest power on x be? If you multiplied it all the way out, you would have x to the third. And you can think of that by counting the factors of x. This first number, -4, is just a coefficient. Looking at this factor occurs one time. And then this second factor occurs 2 times. So we have 1, 2, 3 for a total degree of 3. And then the leading term, if we distributed this all the way out, -4 is out front, then we would have -4x cubed. So -4x cubed is the leading term. A power function of degree n is a monomial of the form a x to the n, where a is a real number that is not 0 and n is an integer greater than 0. Let's graph the following power functions on the same Cartesian plane. So in the calculator, we have x squared, x to the 4th, and x to the 6th. X squared is one that we are hopefully somewhat familiar with. We have our basic quadratic that has a parabolic shape. With x to the 4th, we have a similar shape. We can see that it's still going through -1, 1, the origin, and 1, 1. The graph still looks similar, but it's getting a little bit skinnier, and then closer to the origin, it gets closer to the x-axis. And then when we look at the graph of x to the 6th, again, a little bit similar, a little bit skinnier, closer to the x-axis at the origin. But really what we're focusing on is the end behavior. Notice that all of these power functions have an even degree, and notice their end behavior. All of them point up on the left and the right. In this example, we'll look at different power functions. We have x cubed, x to the 5th, and x to the 7th. When we graph these, we get similar shapes. Again, x cubed we're somewhat familiar with. X to the 5th is a little bit skinnier. Still goes through -1, -1, and close to the x-axis around the origin. And x to the 7th is, again, similar, a little bit skinnier. Goes through -1, -1, closer to the x-axis around the origin, and goes through 1, 1. The main thing we want to recognize here is the end behavior. Notice that all of these power functions have odd degrees, 3, 5, and 7. Look at the end behavior. On the left, the graph points down, and on the right, the graph is pointing up. To summarize this, we have that when n is even, the end behavior is pointing in the same direction. They're either both pointing up or they're both pointing down. Notice when a is positive, that is the leading coefficient, when it's positive, both ends point up. There could be some local maxes and mins in the middle, but the end behavior, we know both ends are pointing up. And then if n is even and the leading coefficient, a sub n, is negative, both ends point down. Again, there could be some local mins and maxes in the middle, but we know the end behavior, both ends point down. And then if n, the degree, is odd, we know that they're going to be pointing in opposite directions. If the leading coefficient is positive, overall, as you read the graph from left to right, the graph is increasing. That is, the end behavior points down on the left, there's some maxes and mins in the middle potentially, and then on the right, the graph is pointing up. But overall, the graph is increasing. And again, if n is odd, but this time the leading coefficient is negative, the end behavior is going to look like this. Overall, the graph will be decreasing. On the left, the graph points up, potential mins and maxes in the middle, then on the far right, the graph is pointing down. Let's look at these polynomials and determine their end behavior. Up first, in example A, we can see that the degree is 1, 2, 3, 4, 5, 6. We have an even degree, which means the same direction. They're either both pointing up or both pointing down. Now we look at a sub n. A sub n is 3, which is a positive number, which means that both ends are going to point up. In example B, we first determine the degree, recognize that we have a 1, another 1, and 2. That gives us a total of 4. The degree is 4. That means same direction. Again, either both ends are pointing up or they're both pointing down. To determine which is which, we look at a sub n, the leading coefficient. In this case, the leading coefficient is a -1. Since it's negative, we know that both ends point down. And then in the final example, n, the degree, is 5. Notice that this is not written in factored form. This one is your standard form. So we just look at that leading term. Degree of 5 is odd, which means opposite directions. But which is which? We determine that by looking at the leading coefficient, -4. Since the leading coefficient is negative, that means overall the graph will be decreasing. So that's decreasing overall. That points up on left and down on the right. So overall the graph is decreasing. Find a polynomial function of degree 3 whose real zeros are -2, 3, and 5. We're going to use the factored form f of x equals x minus r times x minus r, and so on for each 0. So we have f of x equals x minus the first 0. X minus -2 is really x plus 2. Then we have x minus the second 0, which is 3. And then x minus the third 0, which is 5. And from here, we will simply distribute this out. Distributing the last 2 first. So I'll bring down the x plus 2. We get x squared minus 8x plus 15. Then continuing to distribute, we get x cubed minus 8x squared plus 15x. Now distributing the 2, we get 2x squared minus 16x plus 30. And then simplifying once more, f of x is x cubed minus 6x squared minus x plus 30. If x minus r raised to the m is a factor of a polynomial f, and x minus r raised to the m plus 1 is not a factor of f, then r is called a real zero of multiplicity m of f. For example, for the polynomial f, when it's in factored form, we can easily identify the zeros. Notice the first 0 is going to be 0. It's a real zero of multiplicity 2 because of the power on that x. Then the next 0 is -1. It has a multiplicity of 1. We don't see the exponent here, but there's an understood 1 there. It has a multiplicity of 1. And then the last 0 is 3. It has a multiplicity of 4 because the power on that factor is 4. Using multiplicity, we can determine what happens to the graph around those x-intercepts. If r is a zero that has even multiplicity, then the graph is going to touch the x-axis at that x-intercept. If r has odd multiplicity, then the graph is going to cross the x-axis at that x-intercept. In this video, we'll look at sketching the graph of polynomials. Step 1, we're going to look at finding the x and y intercepts. Recall, to find the x-intercepts, we set y equal to 0, or in this case, f we set equal to 0. Notice that it's in factored form, so we can set each factor equal to 0. X equals 0, x minus 1 equals 0, and x minus 3 equals 0. Solving those equations, x is 0, x is 1, and x is 3. So we have our x-intercepts, 0, 1, and 3. Up next, we'll find the y-intercept, and if you notice, the first x-intercept was 0, therefore the y-intercept automatically has to be 0. But if we were doing it algebraically, to find the y-intercept, we simply make all of the x's 0. So we have 0 squared, 0 minus 1, and 0 minus 3 cubed. Notice that that first 0 will give us a product of 0, meaning y is 0. Up next, we will look at end behavior. To determine end behavior, we first look at the degree. N, in this case, is 6. We have 2. The power on this factor, you don't see it, but there's an understood 1 there. That's 3, 4, 5, 6. So adding up those degrees, we get a degree of 6. Notice that that is even. So that tells us that the same thing is happening. So I'm going to make a mental note, same. That means they're either both pointing up or they're both pointing down. To determine which is which, we then look at the leading coefficient, a sub n. Since a sub n is 1, which is positive, that means both ends point up. So we can say that eventually on the ends of the graph, they'll both be pointing up. Next, we look at multiplicity. So let's first look at the zeros and determine their multiplicity. The first 0 is the number 0, and that's generated by this factor, x. Notice its power is 2. That means its multiplicity is 2. The next 0 that we come across is 1. And notice the degree there is 1, so its multiplicity is 1. The next 0 is 3, and its multiplicity is 3. And now what do those mean? The first 0, the first x-intercept, has a multiplicity of 2. An even multiplicity means it's going to touch the graph and turn around. So judging by this end behavior, it's going to start on the left coming down, then it's going to bounce off that point. It's going to touch it and turn around. The multiplicity of the 1, the x-intercept of 1, is odd. That means it's going to cross the x-axis at that point. So we know it's going to cross here. And then the multiplicity on the 3 is 3, which is odd. That means it's going to cross the x-axis at that point. So we know it crosses here. Now we just need to complete these. So on the left, we know the end behavior's got to eventually catch up to this line here. It bounces off due to even multiplicity. And at this point, we know that the graph is going to turn around. There'll be a local max here. We're not quite sure how high it goes without extra work, but for now we'll just say that it turns around. And then down here we know that there's a local min, We're not really sure where without extra work, so we're just going to sketch that there's a min. Then on the far right, we connect the ends. And now we have our sketch. In our next example, notice it's already in factored form. That's going to be helpful for us. To find the x-intercepts, we set the original equal to 0, set y equal to 0, or in this case, set f equal to 0. And that means our first factor is going to generate an x-intercept of 0. It's going to generate this second factor will generate an x-intercept of 4. And then the last one will generate an x-intercept of -2. And since 0 is already one of our x-intercepts, we know that that's going to be the y-intercept as well. So we have 0, -2, and 1, 2, 3, 4. Up next, we'll look at end behavior. First, to do that, we look at the degree. The degree of this polynomial is 2, 3, 4, 5, 6, 7. Adding up those multiplicities, those powers, we get 7, which is odd. That means that opposite things are going to happen. One end will point up and one end will point down. We're not sure yet until we look at the leading coefficient, a sub n. A sub n in this case is -3. Leading coefficient is negative. That tells us overall this graph is decreasing. So on the left, it's pointing up, and on the right, it's pointing down. Notice that there might be some wiggle room in the middle, but overall that graph is decreasing as you read from left to right. Next, we'll look at multiplicity. We'll start by identifying the zeros, and then we'll look at their multiplicity. The first 0, as we read from left to right, is -2. -2 is generated by this factor. Notice that that factor has a power of 2. That means its multiplicity is 2. The next 0 we have is 0, generated by the first factor, which has a multiplicity of 2. 4, which is generated by this factor, which has a multiplicity of 3. The -2 has a multiplicity of 2, which is even, which means it's going to touch the x-axis and turn around at that point. The 0 has a multiplicity of 2 as well. That means the graph will touch the x-axis and turn around at that point. The 4 has a multiplicity of 3, which is odd. That means it's going to cross the x-axis at that point. And from here, we can just connect what we have. On the left, we know that the end behavior will connect with this. And then at some point, this graph has to turn around. We're not exactly sure where. That's okay. We're just going for a quick sketch. Then again, there will be a local max here as well. And then on the far right, these will connect to the end behavior. So we have a very rough sketch of this graph. Again, we're not super accurate with these two local maxes. That's okay. For right now, we're just going for a quick sketch. In this example, we'll start by finding the x-intercepts. To do that, we set y equal to 0. From here, we set each individual factor equal to 0. Notice that the first factor is just a 2. It doesn't have an x beside it. So there's no need to set 2 equal to 0. Just the other factors. X minus 3 equals 0. And x plus 1 equals 0. That gives us an x-intercept of 3 and an x-intercept of -1. The y-intercept is not simply 0 like the last examples because there was no x out front here. So to find the y-intercept, we set each x equal to 0. So using the original equation, make all of the x's 0. And simplifying this, we'll get that the y-intercept is 18. Next, we'll look at end behavior. So first, we need to determine the degree. Going to the factored form, we have 2, 3, 4, 5. Counting those powers, the degree is 5. Since the degree is odd, we know that opposite things are happening. One end is pointing up and one is pointing down. To determine which is which, we then look at the leading coefficient, a sub n. And a sub n is a positive 2. Since it's positive, we can think of the graph as overall increasing. So it's going to be pointing down on the left, and on the right, it will be pointing up. For multiplicity, we start by looking at the zeros, and we can use the zeros of -1 and 3 to find their multiplicity. The first zero, -1, is generated by this factor, which has a power or multiplicity of 3. That means that the graph is going to cross the x-axis at that 0. Odd multiplicities cross. And then our next 0, the 3, is generated by this factor, which has a power of 2 or multiplicity of 2. Even multiplicities will touch and turn around. So at this x-intercept, the graph is going to touch and turn around. And from here, we can connect the rest. So we know that the end behavior will connect up to the -1. Then that will go up and hit a local max at some point. We're not really sure where that local max is, but we know it's there. Then it will turn around and come down to the x-intercept and then go back up to the end behavior. And now we have a rough sketch of this graph. Points of the graph where the graph changes from an increasing function to a decreasing function, or vice versa, are called turning points. Each turning point yields a local maximum or minimum. So if we were looking at this graph has 1, 2 turning points. If f is a polynomial of degree n, then the graph of f has at most n-1 turning points. We want to be careful to recognize that it is at most. We're not saying exactly n-1 turning points, but at most. Also, if the graph of a polynomial function f has n-1 turning points, then the degree of f is at least n. For example, what can be said about the number of turning points of the graph of f of x? First, we need to look at the degree. We can look at the powers on those x's. The first x has a degree or power of 1. Then we have 2, and then another 1. If we add those up, we get a total degree of 4. So that means we have at most n-1 or 3 turning points. If we look at the graph, we can see that this function has one turning point down here at the local min, a second turning point at this local max, and a third at this local min. So in this case, it does actually have 3 turning points. But keep in mind, it doesn't have to. For example, if we looked at the function y equals x to the 10, we know what this looks like. It looks like the power function, kind of like x squared, but much skinnier. It only has one actual turning point. But the definition from earlier says at most n minus 1 or 9 turning points. It doesn't actually have 9, it only has 1. The definition is just a rule that we can use to state at most how many it could have.